Questions about anything? I promised I'm going to post study problems to work on for the exam that's a week from Wednesday in class. I'll do that tomorrow because I want you to concentrate on the current homework set a little bit longer before I give you those problems. Anyway, you shall have plenty of time to think about them, and I'll go over them on the review session next Monday. So last time, we're talking about the Cauchy criterion, which there's a definition of what it means for a sequence to be a Cauchy sequence. And the important Cauchy criterion is that if a sequence that's Cauchy has to converge. The reverse is true, so it's an if and only if thing. It's equivalent to being a convergent series. And that property is the critical property of the real numbers. That's another way of saying that the real numbers are complete. And it's such an important thing that I decided to give this section a 2-lecture treatment. So this is part 2. Last time I studied the sequence defined by we start with a 1 and a 2, and then we start taking averages. So this formula here is for n bigger than or equal to 3. The third one would be the average of the first 2. And the fourth one would be the average of the previous 2, etc. It turns out that last time I showed you that that sequence is Cauchy. So let's see. Let me show you what I did last time. There it is. So step 1 was a simple induction to see that the series terms are all positive, and in fact they're all bounded by 2. That was just an induction. And then the next step showed that the difference between one term and the next turns out to be given by some it's a power of 1 over, it's a power of a half. And I showed you how to do that. Did I? Yeah, I did show that. So I showed why that's true. And then we did this trick, which is an important trick that, so this was the trick that allowed us to show that this is a Cauchy sequence. So if I have an M, it doesn't matter which one of the two, N and M, is the big one. I like to take M to be the big one. So I'm going to look at the difference between xn minus xm, where m is the bigger than n. The trick that's in this section is I add and subtract all the intermediate terms between xn and xm. And then when you stare at those for a minute, you realize that they sort of pairwise, they do pair. I'm adding and subtracting, so they pairwise cancel just by what I'm doing. But when I look at that and do the triangle inequality, I can estimate the difference between xn and xm by all the intermediate differences. That's just the triangle inequality there. And I have a formula for those differences. They're all powers of 1/2. And so I write them out and realize, oh my gosh, that's a geometric series. And I have a formula for the sum of a geometric series, which, by the way, I stupidly wrote down wrong last time. I go back and fix my notes after each lecture. So I had the geometric series formula. It's 1 plus r squared plus etc. out to r to the n. Last time I wrote 1 minus r to the n on the numerator. It's 1 minus r to the n plus 1 in the numerator divided by 1 minus r. So I fixed that. And so knowing that formula allowed me, after factoring out the first power there, to express that sum as a very finite thing, and there it is. And that's when you calculate that and clean it up, that difference between xn and xn minus xm, absolute value, it's less than 1 over 2 to the n minus 2. And of course, that goes to 0 rapidly. And so I can make that less than any epsilon I want. And notice that the m doesn't appear in that formula. So m can be arbitrarily large. And so that's true for all n and m. I can make it as small as I want. So that's why it was Cauchy. And then, so the fact that it's Cauchy implies it converges to. And I did a trick that we've seen work in the past. If you know the if you know that a series sequence converges, and it's given by some recursion formula, when you take the limit in the recursion formula, of course, xn plus 1 converges to the same limit xn does. And so does xn minus 1. So I write that out and realize, oh, I get a formula. Unfortunately, the formula is L equals L. And so it doesn't give me any insight into what the limit is. And so I thought I'd finish off today and show you that the limit is 5/3. Questions about anything from last time? Or that example? That's a fun one. So if you analyze this sequence further, it turns out that the odd terms are strictly increasing, and the even terms are strictly decreasing. If you think about it, 1, 2, the next one's 3/2. Okay, that's less than 2. And then the midpoint of 2 and 3/2 would be 3/4. That's a little bit bigger than 3/2, so it's going up and down and up and down. And if you were to graph that, you realize, oh, the odd ones keep getting bigger and bigger, and the even ones keep getting smaller and smaller, and they squeeze into the limit. So the question is, what is the limit? We know it's Cauchy. Cauchy implies that L exists. Okay. Well, the book shows you that the odd terms you can do by an induction. Induction. It's not hard. I won't do it. Every now and then I do one just so you get in a habit of doing them yourself. The odd terms are determined, and they're given by x 2n plus 1 equals 1 plus a half squared plus dot 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 out to 1 over 2 to the 2n minus 2. And the book says you can calculate that, and you can. So let's see. Let's calculate that exactly. Let's see. The 1's okay. I can pull out the half. Oops, what is this thing? 1. I'm sorry, I didn't write this down right. It's 2 1/2 plus 2 to the 2 cubed plus 1 over 2 to the 5th, the odd powers of 2. And the last one is 1 over 2 to the 2n minus 1. That's an odd number. How do you figure out what that is in the limit? Here's how I figured it out. I have 1, I'm going to leave that there by itself, and then I'm going to factor out a 1/2. And that gives me 1 over 1 plus 2 squared plus 1 over 2 to the 4th plus etc. out to 1 over 2 to the n. Let's see, here's the trick to realize what the heck that is. This is 1 over 2 squared to the 1. This is 1 over 2 squared squared. This one is 1 over 2 squared to the n. And so this is equal to 1 plus a half times 1 plus a fourth squared. Another geometric series is popping out at us. Plus 1 over fourth to the n. And so let's see, that's equal to 1/2 plus 1. The sum of that geometric series is 1 minus 1/4 to the n plus 1. This time I wrote it down right. Over 1 minus a fourth. And notice as n goes to infinity, 1/4 to the n plus 1 goes to 0, because 1/4 is less than 1. And so this tends to 1 plus a half times 1 minus a big fat 0 right there, divided by 1 minus 1/4. Clean it up and it's equal to 5/3. So when you're desperate to find a limit, quite often you can figure out some sneaky thing to do. Questions about that? Is it 5? Yeah, it's 5/3. Yeah. The odd terms equation? The first one.
Yeah, if you have 2 and minus 1, when you pull out a 1/2 on the next line, would it be
Oh,
plus?
it'd be 2n minus 2. Okay, thank you. Oh, you're the, you're the one who always is finding my errors in the geometric series. There's another error. So this would be n minus 1. And this would, yeah, this is n minus 1. And look at that, makes this even nicer. Oops. Thank you for watching closely. Other questions?
If it's even terms, it would be as the same amplitude.
I assume the even terms can be handled similarly. But here's an important thing. I wanted to say, the book is always saying, why, show this, why, etc. I just found you a subsequence that converges to 5/3. And I know that the series converges. That means it has to converge to 5/3 because every subsequence converges to the limit. So here's what the book does. The book says, so L equals 5/3. And then, of course, they say why, because they want you to think about that. The reason is because when a series, we know Cauchy implies converge. We know Cauchy implies converge. We also know that every subsequence of a convergent sequence converges to the limit. Every subsequence of a convergent sequence. That was one of the facts from the section with the Bolzano-Weierstrass theorem. To the limit L. So in this problem, L is 5/3 because we found a subsequence that converges to something. Now, if that means that the even ones would also have to converge to that. They just have to. So we don't have to check them. By the way, that trick I did, the reason I dwelled on it is because that trick of doing xn minus xm is less than or equal to xn minus xn plus 1 plus etc. Plus x m minus 1 minus xm is handy because it allows us to prove what is this called? I guess it doesn't have a name. To prove this. I'll make a definition here. A sequence x to the n is called, x sub n is called contractive if it squishes things together. Okay, so the condition is xn plus 2. These just have to be consecutive terms. The index is kind of arbitrary what you pick. That is less than or equal to a constant c times xn plus 1 minus xn. So each consecutive pair of terms is going to get a little bit closer together by a factor. So this is going to be for all n. It actually only matters if it starts holding for the tail end of the sequence. A few terms in the beginning that are weird don't matter. It eventually has to hold. But this is the definition in the book. It's important to say where c is a positive number. It'd be kind of dumb if it was 0. But this is an important part, is it has to be less than 1. That's what the contraction is all about. Things are getting squished together by a factor, and the factor is less than 1. Well, that allows you to estimate that that sum, the telescoping sum, because consequently, let's see, I would have xn plus 2 minus xn plus 1 would be less than or equal to c times xn plus 1 minus xn. And then I would use it again here, and this is less than or equal to c times the next one down. That would be xn minus 1. And I can do it again. This one would be less than or equal to c times the next one down. Let's see, that'd be xn minus 1 minus xn minus 2. And dot, dot, dot. I would see that if it's less than or equal to c to the n. When I get to the last one would be x2 minus x1. So I do it n times and get that. And that's exactly what allows me to compare that term in a Cauchy sequence to a convergent geometric series. So So the aha, compare xn minus xm, exactly like we did in the 1/2 to the n case, to what would it be? Yeah, when you start doing it, you'd get c to the n minus 2 plus, etc., c to the n minus 3 plus dot, 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 plus c to the last one. Which one's the big one? Oh, this would be, I'm sorry, this would be m. That's the big one. Anyway, I went through the details above, and so I'm not going to do it again. Let's see, the last one would be c to the n minus 1. And they'd all be times this thing. And this would be this is the limit of a geometric series. In fact, I'd analyze it exactly the same way. I'd pull out the smallest power. This would be a geometric series. And the fact that c is less than 1 means that this would converge to something. And it'd be just like the example above. And so I can make this small. Exactly as in the example about the averages. So I won't do it again. Okay, but the upshot is that there's a theorem called the contraction. I guess it doesn't have a name. There's a thing called the Banach contraction principle that's very related to this. But they don't give this thing a name. The theorem is every contractive sequence converges. Just because it's Cauchy, and therefore it converges. Every contractive sequence must converge. And so the reason is because it's Cauchy. That's why it's in this section. Questions about that? Well, one of the reasons I wanted to dwell on this section is because this next example is one of the fantastic things in math. Everybody's crazy about the Fibonacci numbers. And they came up in the history of art, and Da Vinci and Michelangelo, and they're incredibly cool. So, I want to talk about Fibonacci numbers and the golden ratio. You've seen pictures of the Nautilus repeating pattern and heard these words before. The golden ratio is -1 plus the square root of 5 over 2. And let's see, you've seen, what's the famous picture? You have a rectangle. Then you make this square here. Oh, that's not a golden ratio. Make this square. And this rectangle is similar to the original rectangle. You make a square here. And my golden ratio is kind of crummy. That's a square. Then this ratio is this little rectangle is also similar to the previous two rectangles. And you keep repeating that. Where am I supposed to put the next one? Probably here. Etc. And this number comes up when you analyze that sequence. And it's the golden ratio, and some famous paintings place things in the painting by thinking about where the golden ratio lines up. Anyway, that's the geometric way of thinking about it. But the Fibonacci numbers are given inductively. Let's see, the first two Fibonacci numbers are 1 and 1. They both equal to 1. But starting at n equals the next one, I'll say starting with n equal 2, the next one, that would be 3, xn plus 1, is just the sum of the previous, oh, I'm not going to call these f's. Fn plus 1 is the sum of the previous two. So in that example I did, I was taking averages of the previous two. The Fibonacci numbers are the sum of the previous two. And of course they get bigger and bigger. They're all bigger than n. Let's see, no, f3 is 3. I mean, f3 is 2. But eventually they start getting bigger and bigger. That wouldn't be hard to show. So they go off to plus infinity. That's the next section. We're going to talk about tending to plus infinity. So they certainly don't converge to a number, unless you think of converging to plus infinity as a thing, which we will. But the famous thing is to look at the ratio of the, let's let xn be the ratio of the nth Fibonacci number to the next one. That's less than 1 because they're getting bigger and bigger. Okay, here's a cool thing to think about. Now we're thinking about a new sequence. Let's think about what xn plus 1 is. It would be fn plus 1 over fn plus 2. And fn plus 2 is just the sum of the previous two. That would be fn plus 1 plus fn. And now I multiply that on top and the bottom by 1 over fn plus 1. And when I do that, I see this is equal to 1 on the top, and on the bottom I would get 1 plus fn over fn plus 1. And that's when you say, aha, that's equal to 1 over 1 plus xn. So the ratios of the Fibonacci numbers, well, let's see, before I did this, okay. So those ratios of the Fibonacci numbers satisfy a different kind of recursion formula. Xn plus 1 equals 1 over 1 plus xn. Words for that. I would say this is recursively defined, and there's the recursion formula. You get the next one from the previous one. Sometimes recursion formulas require knowing all the previous ones. They're more complex. This one's a very simple one. So I call that kind of like when you study ODEs, solve power series methods in ODEs. You get a recursion formula. Okay. And maybe this is, I should have called this a step 0. A simple induction shows you that those ratios are squeezed, or they're not squeezed, they're just bounded between a half and 1. That's an easy induction. So it's because the Fibonacci numbers are getting bigger and bigger, and so those are getting smaller and smaller. Are they? I take that back. I don't know what I'm talking about. But this is a true inequality. And therefore, when I add 1 to both sides, I get half plus 1 is less than or equal to 1 plus xn is less than or equal to 1 plus 1. And now when I take the inverse of that, that would be 3/2, so 2/3 would be greater than or equal to 1 over 1 plus xn is greater than or equal to 1/2. Okay, that's the inequality I want. And now I claim that that's going to allow me to see that this sequence is contractive. Claim xn is contractive. Okay, here's the trick. The reason I'm doing this is because the book doesn't tell you quite how they did it. All right, so I'm going to take xn plus 1 minus xn. I want to show that's greater or equal to, less than or equal to c times the next one down. So let's see. Here's what the book didn't write. That's 1 over 1 plus xn minus 1 over 1 plus x sub n minus 1. And now you cross multiply that stuff there and get 1 plus xn minus 1 minus 1 plus xn on the top. And at the bottom you get product of the things in the denominator. And notice the ones on the top cancel, and you're left with, it's xn minus 1 minus xn, but that's the same as the absolute value of xn minus 1. And on the bottom, well, these things are all positive, so I don't have to put absolute values. Okay, and I put in a red box that inequality. Those 1 over 1 plus xn's are all less than or equal to 2/3. Right. So equal to 2/3. So they're also greater or equal to 1/2. Yeah, that's the one I need. Those things on the bottom aren't getting too small. I want to make this less than something. So I need a greater than or equal to inequality in the bottom to get that this is less than or equal to xn minus 1 over a half times a half. Those things are greater than or equal to a half. What? Am I screwing this up? T halves 2 is less than or equal to 1. Or equal to. Where is it? Less than or equal to. I screwed something up. I'm sorry. I can fix this. Okay. 1 half is less than or equal to xn is less than or equal to 1. 3 halves and when I reverse the thing, I get 1 over it is 2/3. That's correct, isn't it? What?
And after that, the C, the constant C,
Yeah, I need something less than 1. Crap, did the book make a mistake? I didn't even think about why this could be wrong. Taking, so because it's the inequality. Less than or equal to. 2/3. I add 1 gives us 3 halves is less than or equal to. Oh, stupid. I don't know what's wrong with me. To get the inequality going the right way, I need the 2/3 ones here. Two-thirds. Oh, 1. I see what I'm doing. I'm sorry. All right. 1 over it is the thing in the denominator is less than or equal to 1 over the thing in the denominator is less than or equal to 2/3. All right. And that's the one I need. And that's 4/3. That's 4/9, which is less than 1. And so, yes, it is contractive. And that means that theorem implies that it's Cauchy, and so the xn is Cauchy, and it converges. So xn goes to a limit. And the question is, what is L? Well, all those xn's are positive, so that whatever it is, it's a positive number. So since all the xn's are bigger than a half, in fact. L is bigger than a half. So we know that at least. It's also less than 2, or less than or equal to 2. Well, here's the thing. When you've got a recursion formula, you always realize that xn plus 1 is 1 over 1 plus xn. And so in the limit, that's going to tend to the right-hand side would be 1 plus L, 1 over 1 plus L, and xn plus 1 would converge to the same limit. So I'd get L here. And of course, the denominator is never 0, and the limit exists and is not 0. So the quotient of a limit, the limit of a quotient is the quotient of the limits. I'm using that fact. But now, for once, I get a formula, I get an equation that I can solve for L. So great, this is better than the previous example where I got L equals L. This time I get L squared plus L minus 1 equals 0. And the quadratic formula tells me that L is equal to minus 1 plus or minus b squared minus 4ac over 2a. There's 2 of those. One is square root of 5 minus 1 over 2, and the other is minus the square root of 5 minus 1 over 2. So that one's greater than 0, and this one's less than 0. Well, that can't be our limit, because our limit is positive. So this one is out. And so that leaves that L must be that other one. Square root of 5 minus 1 over 2. The famous golden ratio. So the golden ratio is the limit of the ratios of the one Fibonacci number to the next. That's a cool thing. Sorry I got disoriented there for a second. The reason I was screwing things up is because I wasn't looking at those things as 1 over 1 plus xn. I was looking at them as the thing in the denominator. I have to pull them out and use the right inequality to get that 2/3 times 2/3 thing, which took me a minute to realize. Questions about that? That's kind of a beautiful application of this material, I think. So there's one more section in chapter 3, and it's the business about going to plus infinity and minus infinity. And I'll spend the last few minutes here talking about that. So the first exam is in class on Wednesday, February 28th. I'm going to allow you to bring one crib sheet, one two-sided, standard size piece of paper crib sheet, handwritten only, so you can't laser print something microscopic. You can write on both sides. That should be plenty, I think. You could write half the book that way. So it's closed book, closed notes, except for that crib sheet. Closed books, notes. No electronics, which means no calculators. You won't need a calculator because everything will be simple when it comes to the arithmetic. And I'll supply the paper. So I'll only need pencils and erasers. Okay. And the exam covers everything up through this next section, covering all the book section, chapters 1, 2, and 3. Which is up to 3.6, which I'll talk about next time. That means after exam we can start with chapter 4, which is about functions and limits of functions, which is good stuff. So section 3.6, it's called properly divergent sequences. And that means sequences that the limit as n goes to infinity of xn is equal to, there's two cases, plus infinity and minus infinity. Okay. So plus infinity means the sequence gets eventually bigger than any given natural number. And going to minus infinity, it means eventually getting less than any gigantic negative number, no matter how gigantic and negative. So words, definition, we'll say limit as n goes to infinity, xn equals plus infinity, means given an m bigger than 0, no matter how big, there is an n natural number. The book likes to write n depending on m, such that the terms are bigger than that from that point on, such that xn is bigger than or equal to m for all n bigger than or equal to n. And an example, you show it by induction, that if fn, the nth Fibonacci number, is eventually bigger than n. So an example, make it our first example, the limit of the Fibonacci numbers, infinity. So infinity means plus infinity. Interesting thing, in a complex plane, infinity means the point at infinity. But in real analysis, infinity means plus infinity. And we'll use minus infinity for the other one. Okay, so I have 30 seconds. The definition of limit as n goes to infinity of xn equals minus infinity. It'd be the same thing, but you reverse the inequalities and you take m to be gigantic negative numbers.